Okay, so this is 16.7, part 3, still talking about surface integrals, but this time we're going to start looking at surface integrals of vector fields. So in order to do that, we're going to start our conversation discussing oriented surfaces. And oriented surfaces just mean that there are essentially two sides to the surface. And because there are two sides to the surface, we have to kind of distinguish, like, what is this correct? What is the proper orientation? What is the expected orientation or conventional thinking for the orientation of our surface? So this is just a visual for the two sides of the surface. But our vector n, which try and remember what that vector represents, right, is going to give the upward orientation. And so negative n will give the opposite orientation. And I've defined n here, right? So we have that. And so in order to just give you some background or, something tangible to kind of relate this to, I decided we could think about a sphere. Doesn't matter what the radius is. You'll notice I just have A in there for the radius. So just to kind of relate it back, these items here in purple are all things that we've discussed in previous sections. So I have my, parametric, right? I have my three components for my vector function. I have the cross product with my partials, right? So I have those in there. We did this already. I have the magnitude of that cross product, and I have a squared sine phi. So if I think about how that relates back to n, the unit normal vector, right? I see that it's just going to be 1 over a times my vector r, my vector value function r. So that indicates to us that it points outward from the sphere, and this is the conventional thinking for any closed surface. So the conventional thought is that the proper orientation is pointing outward, essentially, from the surface. So if you think of a sphere, it would be pointing away from, out of the sphere. Into the sphere would be the opposite orientation. So it's just a little bit of background in terms of just the idea of an oriented surface, relating it to vector fields, so that we can start to look at some more problems related to surface integrals with vector fields. So I want to just bring you back first to content that we discussed in previous sections relating to line integrals. We already talked about this idea that line integrals, we have this familiarity with it, so our knowledge from line integrals can help us to relate to surface integrals. So I just wanted to remind you of this statement in purple. Is something that we had discussed in previous sections. The line integral of the normal component of f along C is equivalent to the double integral of the divergence of f over the region D enclosed by C. So we're going to start to use that to kind of incorporate some information with our surface integral and see how that kind of relates. So if f is a continuous vector field defined on S with the unit normal vector n, then the surface integral of f over S is actually going to be equivalent to this, which is referred to as the flux of f across S. We're going to take that and we're going to start to piece it out so that we can come to a more helpful conclusion, something that we can use when we go to do problems. Okay, so we're going to start with this, and we're going to start to substitute some stuff in so that we can get it down to something a little easier for us to actually evaluate. So what I'm going to do is, I told you what n was a little while ago, right? We have this. I'm going to plug that in for n here. Okay, so I'm going to have double integral over S, F, dot it with, instead of N, I'm going to replace it with the R sub U cross R sub V over the magnitude. So that's all I've done first, is to just replace N with its equivalent, cross product over the magnitude of the cross product. The next thing I'm going to do then is I'm going to replace ds, which we've done in previous sections and even in this section, right? We've talked about, we're going to replace that with the magnitude of the cross product dA. So we've seen that in earlier videos. Now, when I do that, I should actually replace S with D, right? Because that's what we did before. And I'm really doing the vector field of R. So it's going to look like this. I'm going to have F of R of UV, dot it with, and then I have this here, same thing that I had before. But I'm replacing, and this is really in parentheses, I'm replacing ds with the magnitude dA. Well, that's really interesting because that's the same as this. So those are essentially going to cancel out. So this is what we get for our final thing here. Double integral over D, F evaluated at R of UV, dot it with our cross products, dA. And that's the one we want to keep in mind as we move through our examples. So I'll give you some time to copy that down. So we're going to use that to work through 2 examples for today. I'm going to skip a lot of steps and things that are, things that we've already covered in previous sections, like just not the conceptual stuff, but the mathematical part. Again, feel free. You can pause the video, you can complete it yourself, and then you can pick up the video and see that it's the same thing. So I'm going to try to keep that just right at the top there for us so we have it. But here's our first example for today, example 4, continuing on from our previous videos. We want to find the flux of the vector field across the unit sphere. So I'm going to start first with my vector function, r of phi theta. We've done this in previous sections. It's a unit sphere, so A is just 1. So I'm going to have sine phi cosine theta, sine phi sine theta, cosine phi. For my double integral, though, I'm going to want to do f of that, right? And here's f was given to me. So if I do f of r of phi theta, so I want z, so I want this part first, so cosine phi. Then I want y, so that's just going to copy down. And then I want x. So it's really just a different order because it's just happens to be what f is for us for this example. The other thing that I'm going to need is I'm going to need my cross product. Again, this is something that we did in previous work. So if I wanted, again, sit there and find my partials, complete the cross product, that this would be a time for you to pause the video and try those again. But I have sine squared phi cosine theta, sine squared phi sine theta, sine phi cosine phi. Now I'm going to do the dot product of those two. It's going to get messy, that's for sure. Okay, so now I'm doing the dot product So I'm doing F dotted with my cross products. So this is what I end up getting. It's a dot product, so it's not going to be a vector. It's just going to be a scalar quantity. So I'm going to get cosine phi sine squared phi cosine theta. Right? I'm doing the dot product of these two. Then what am I going to get? Sine cubed phi. I should not have a comma there, right? Making sure I'm not making mistakes. Sine cubed phi sine squared theta, right? Plus, and then sine squared phi cosine squared, cosine theta and cosine phi. So cosine phi, cosine theta. Those phi's and thetas, they look so similar sometimes, so just be cautious because clearly I just made that mistake. You don't want to make that mistake just because you're writing so quickly. Okay, so I'm going to go ahead and put this into my double integral, and you're actually going to see that it's not as terrible as it seems. Right now it seems like it's going to be such a doozy. It's really not that bad once things start playing out. So I have my double integral over d. My variables are phi and theta, so I know those bounds, right? So it's just 0 to 2 pi, 0 to pi. And if you notice, the first and third piece of my dot product is the same. I don't know if you noticed that. So it's sine squared phi, cosine phi, and cosine theta. It's the same three, just in different orders, but it's multiplication. So it's actually 2 sine squared phi, cosine theta, plus sine cubed phi, sine squared theta. And then I have d theta, d phi, d theta. Can you tell this is the last video of the day? No? Okay. All right. So what I want to think about is if there's a way for me to kind of simplify this up a little bit. So remember, it's always helpful if you can separate. So the first thing that I'm going to do is I'm going to treat these two separate, obviously, because I have the plus sign in between. So I'm just going to think of them separately. And then within each of those individual integrands, I can split up the phi and the theta part because I can separate them by multiplication. My bounds, I don't have one bound dependent upon the other variable. So I'm able to do that. So essentially I have just this part first. So all I'm doing first is I'm separating the plus sign. So I have sine squared phi, cosine theta, d phi, d theta, plus, and then I'm going to do this again. I don't want to skip steps there because I don't want to, that's not necessarily the math. That's just... Then what I can look at is the fact that I can separate this so that it's just one integral with cosine and one integral with phi. So I'm going to have a 2 on the outside. It's all multiplication, so it's not going to matter. 0 to 2 pi cosine theta d theta, and then 0 to pi sine squared phi cosine phi d phi. I'm just looking at that first part. And then same thing with this second piece, I can separate it. So I can do 0 to 2 pi sine squared theta d theta, and then 0 to pi sine cubed phi d phi. What's helpful about this is hopefully you can see that this part right here is just going to be 0. So I'm going to have cosine theta. When I integrate that, right, I'm going to get sine theta. And I'm going to evaluate that at 2 pi and at 0. And that's just going to give me 0 minus 0. It's just going to be 0. So this goes to 0, which means this entire thing goes to 0 because it's 0 times something else. So I'm only concerned with this part. So it's really helpful because it looks like it's going to be really complicated, but that entire first half, which is more complicated, just disappears. Now, I'm not going to go through this integration because this is very much like example 1, where we use the identities. We'd want to replace sine squared. It's just negative. Remember in our other example, in example 1, I think we had cosine squared, right? And then we had the sine cubed in the other example as well. So it's just a matter of going through those motions, very much like we did in example 1. And when you do that, you should get 4 pi over 3. So this is very similar. It's not exactly the same to example 1. So again, I'm going to kind of skip going through all of those motions in an effort to save time on the video. But for your work for today, since all you have to do is watch the video, you can kind of pause it, make sure you can evaluate that integral. If this is a velocity field describing the flow of a fluid with density 1, then the rate of flow through the unit sphere is 4 pi over 3 units of mass per unit time. So that's kind of a cool connection. So for our second example for today, we're going to be looking at the other scenario. We've seen this a couple of times where we're now looking at S being defined by, it's some function of x and y, so we let z equal that x or y function. So a couple of things in order for us to kind of calculate almost like a formula today for this type of problem is going to look a little different. Remember, we're going to have f dotted with our cross product. Right, so what is that going to look like? F is going to be, remember we've used this before, P, Q, and R. Those are just general letters for some functions of x and y, or x, y, and z. And then you're going to have your cross product here. But remember, x is just x, y is just y, and z is some function of x and y. So think about what each of those partials are going to be. Think about the cross product. We've done this before. Again, if you want to pause the video and go through and do this, you should get this as your cross product. We've done it in previous videos. So if you'd like to sit through and try that, you can. So then what does that tell us about our double integral over S of f dot ds? This time, it's going to be the double integral d, and we're doing the cross product of this, so it's going to be negative p del g del x minus q del g del y plus r. So that's kind of our other formula if the scenario presents itself a little differently. So here's an example that does that. So you have this example, evaluate the double integral over S of f dot ds, where here's your vector field F. S is the boundary of a solid region E enclosed by a paraboloid, and Z equals 0. So one thing I might just want to do here is set these two things equal to each other just to kind of see what happens there. And when I do that, right, I get x squared plus y squared equals 1. So I'm going to keep that in mind. So what do I have here then in terms of my P, Q, and R? I have to define my P, Q, and R, right, for this. Well, I'm given F, right, is right there. So P is just going to be Y, Q is going to be X, and R is going to be Z, but Z is 1 minus X squared minus Y squared. So then I want to find, in order to use my formula, I want to find del G, del X, del G, del Y. So I'm going to find those using this, right? So I have del G, del X is going to be negative 2X, right? My partial with respect to X. And del G, del Y is going to be negative 2Y, my partial with respect to Y. So if I want to start plugging in, so what am I going to have here? I want to keep in mind like my formula, right? Negative P del G del X minus Q del G del Y plus R. And I have my P, Q, and R, just trying to get everything on the screen there for you. And I have my partials. So I can start to plug some stuff in. I'm going to plug everything in before I do my bounds, right? It's always helpful to kind of save the bounds to the last part, because then if you want to convert to polar, you don't have to worry about filling in those awkward bounds first. So what am I going to have here? Negative Y times negative 2X minus X times negative 2Y plus R, which is 1 minus X squared minus Y squared. So I'm just going to clean that up. So I'm going to have 2xy plus 2xy plus 1 minus X squared minus Y squared. So I have 1 plus 4xy minus X squared minus Y squared dA. And again, I know it might not necessarily seem it right away, but I think a conversion to polar would be helpful. So let's try that. We have our bounds 0 to 2 pi, 0 to 1. So remember we did the x squared plus y squared equals 1. So I'm just replacing, so I have 1 plus 4. Instead of x, I'm going to have r cosine theta, and then instead of y, I'm going to have r sine theta. So it's going to be 4r squared cosine theta sine theta. And then I have minus x squared plus y squared, which is r squared. But then I need my Jacobian, my extra r, dr, d theta. So, I mean, this is a pretty straightforward integral to solve. I would just distribute my r. So I'd have r plus 4r cubed cosine theta sine theta minus r cubed dr d theta. You're integrating with respect to r and plugging in your 1 and 0. And then you're integrating with respect to theta, and it's a pretty straightforward u substitution. So you should get, as your final answer, pi over 2. So again, maybe pause the video, do that integral, see if you can evaluate it. The disk is oriented downward, so the unit normal vector would be 0, 0, negative 1. Okay, and that's all I really have for 16-7. All right, so we can start trying some of those homework problems and see how we feel.